Today we're going to learn the technique of implicit differentiation. It's used when the equation for a curve is not written in the typical way that we see it, which is called explicitly, which is y equals some stuff with x's in it. So when it's not written that way, we can use this new technique rather than solving for y. Okay, so I will give you a little bit of time to look over test number 2 next class, since it's not done yet. Don't know yet. Don't know yet, but probably not. Okay, so let's start with our demo on implicit differentiation. I want to find an equation for the tangent line to the curve x cubed plus y cubed equals 3xy at the point 3/2, 3/2. So I've graphed the curve here, right? This is called the Folium of Descartes, famous curve. The point 3/2, 3/2 is right here. So I want to find the equation of the line tangent to the curve at that point. Right, so I'm looking for the equation of this line. Yeah, so it looks like, just from like the looks-at theorem, it looks like it's got a slope of -1. Yeah, but let's verify that that's the slope. So how do you find the slope of a tangent line? You find the derivative. But all of the derivative rules that we have assume that the function is written in y equals some stuff with x's in it format. We could try to solve this thing for y. It would be a big mess, right? I'd end up taking a cube root. Yeah, it would be kind of a mess. Yeah, so instead, I'm going to introduce this new technique where I have x cubed plus y cubed equals 3xy. So my new technique says take d dx of both sides of this equation. It's allowed, as long as you do the same thing to both sides, the equation stays true. So I'm going to take d dx, the derivative with respect to x, of x cubed plus y cubed, and d dx of 3xy. Now, what's important to remember here is that y is not a constant, right? Y is a function of x, right? Y depends on x, because I could take this thing and solve it for y, right? And y would be a function of x. So y is a function, not a constant. All right, so let's try to take the derivative of both sides here. D dx of x cubed. What's the derivative of x cubed? 3x squared. Okay, that part's easy. What is the derivative of y cubed? 3y squared is the first part of it. Yeah. And if this said d dy of y cubed, then it would just be plain old 3y squared. But it's d dx. Yeah. It's a derivative with respect to x. So it's 3y squared, but then I have to multiply by the derivative of the inside function, right? Y is a function of x. So I have to then multiply by y prime, the derivative of y. That's what we want to know, right? We're trying to find the slope of this tangent line. We're trying to find y prime at the point 3/2, 3/2. So I don't know what it is yet. All right, and then d dx of 3x times y. How do you take the derivative of a product? Yeah, it's going to be the product rule. So we'll call this guy the first, and we'll call this guy the second. Yeah. So first, 3x, times the derivative of the second. What's the derivative of y? Y prime. Plus the second, y, times the derivative of the first. The derivative of 3x is 3. Okay, so I'm going to go through and finish this, and then I'm going to do a little bit more explanation afterwards about the 3y squared y prime thing, because I know that that's the big sticking point in this problem. So now what I want to do is I want to solve this thing for y prime. I want to solve this equation for y prime. Because that's what I need. To find the slope of a tangent line, I need y prime. So any term that has a y prime in it, I'm going to keep on the left. And every term that does not have a y prime, I'm going to put on the right. So I've got 3y squared y prime minus 3xy prime equals 3y minus 3x squared. Any ideas on what to do next? Trying to solve for y prime? Mm-hmm. Yeah, we do want to, the problem is I have two terms of the y prime in there, right? So I could factor out a y prime. So I'd have y prime times 3y squared minus 3x. Yeah, I could just divide both sides by 3 and get rid of all my 3's. Maybe I should have done that in the previous step. So y squared y prime minus xy prime equals y minus x squared. Just divide every term on both sides by 3. Then on the left side, I can factor out my y prime. Y squared minus x is y minus x squared. And then to get the y prime by itself, divide by this thing that's being multiplied by y prime. Y squared minus x. So I have y prime is equal to y minus x squared over y squared minus x. All right, so how does that help me get the slope of the tangent line at 3/2, 3/2? That's the derivative of the function at any given point x, y. Now I could plug in the x and y values, the 3/2 for x and the 3/2 for y. Yeah, that's the one additional thing you need when you do implicit differentiation is you need the coordinates. You need both coordinates of that point of tangency, not just the x coordinate. Right. All right, so the slope of my tangent line is going to be y prime evaluated at 3/2, 3/2. So I'm going to have 3/2 minus 9/4 over 9/4 minus 3/2, which is -1. You were right. Okay, so that's the slope of my tangent line. Running out of a little room here. How do I write the equation? I know the slope. What else do I need? 1 point. 1 point with 2 coordinates, an x and a y. Do we know a point on that line? Yeah, what are its coordinates? 3/2, 3/2. The point of tangency. Right? This point is on the line. And I know the slope of the line is -1, so I can write the equation of the line. Do it on another slide. So I know my slope is -1, and I know my point is 3/2, 3/2. So the equation of my line in point slope form, which is the one I like to use because we often have the slope in a point. So this is going to be y minus 3/2 equals -1 times x minus 3/2. And there's my equation. And if you don't like point slope, you could solve for y and get slope intercept. So I'd have y equals -x. That's it. Plus 3 plus 3. So does it look like that's the equation of the line? Does it look like it's going to have a y-intercept at 3? Seems reasonable based on my hand sketch here. Slope of -1, y-intercept of 3. All right, so let's talk about the this first step here, this d dx of y cubed. All right, so y is really a function of x, right? Y is really a function of x. So if I want to take d dx of y cubed, I'm really taking the derivative of f of x cubed, right? And this is the kind of thing that you did on your last test, right? If you want to take the derivative of f of x cubed, you take 3 times f of x squared, right? But then you still have to multiply by the derivative of the inside, f prime. And now I'm just using a y instead of an f of x. So that's why I had 3y squared y prime. So you're using the chain rule. When you take d dx of some stuff that has y's in it, you're using the chain rule. Okay, so if you have an equation that you cannot solve explicitly for y, we say the equation defines y implicitly. The technique we just used is called implicit differentiation. You know you need to use this technique if your equation has x's and y's like all jumbled together, and it would be hard to solve for y. So when you're differentiating implicitly, just remember that whenever you're taking a derivative of a term that has a y in it, you have to multiply your derivative by dy dx or y prime from the chain rule. That's why the 3y squared times y prime. Just don't forget the chain rule whenever you're taking the derivative of something with y's in it. Okay, you can try some.